Hello and welcome to the second half of Math 151. For these next two note quizzes, we're going to focus on polynomials, and to do that, we're going to start off with first talking about quadratic functions, which are going to be graphed as parabolas. Now, in previous note quizzes, we saw that this is the squaring function, and we know that the general shape is a parabola that can be transformed into many different widths and moved around and reflected around the x-axis. So let's kind of have that approach for this problem here. So the first thing you want to notice in this problem here is that when you graph it, it's going to be opening downwards because we have a negative reflection across the x-axis. So we're going to go through and first get the vertex for this quadratic function. And to kind of foreshadow a little bit, the formula for the vertex is going to be coming from the form of the quadratic function. And so when you have a function of the form f of x is equal to a times x minus h squared plus k, a person who knows a lot about quadratic functions can read off the vertex very easily by just looking at the two numbers h and k in the formula. And so the h number is going to be the x-coordinate of the vertex, and the k number is the y-coordinate of the vertex. So this right here is going to be the vertex for this quadratic function. And on a graph, it's either the highest point of the parabola when it opens downwards, or it's the lowest point of the parabola when it opens upwards. So because, again, we have a negative 2x, we know that this parabola is going to be opening downwards. So we know it's downwards, and we will write that over here in our answer space. A vertex, again, is going to be that h and k ordered pair. So the h number is 3. You'll notice the minus is a placeholder, so it's always the opposite of the number following the x. And then the k number is exactly the number that occurs behind the square. So it's going to be 3, 2. 2, I said, not 3 again. There we go. Anyways. So next thing I talk about here is the axis of symmetry. We'll see this in the graph in a few minutes here, but that is a vertical line that divides the parabola into two equal halves that passes through the vertex. Because it's a vertical line, it must always have an x equals, and because it passes through the x-coordinate of the vertex, it's x equals 3 in this case. The next thing to do is talk about x-intercepts. Not all parabolas are going to have them. It depends on where they're located on the graph. But for us, the x-intercept is going to be the same thing as just setting the function or the y equal to 0. So we're going to set the y or the function g of x in this case equal to 0. So that's going to be negative 2 times an x minus 3 squared plus a 2 equals 0. Subtracting 2 from both sides, we get negative 2 times x minus 3 squared equals negative 2. Dividing both sides by a negative 2 is going to give us x minus 3 squared equals 1. We can now use the principle of square roots to take the square root of both sides. And so that's going to give us x minus 3 equals plus or minus 1. So x is going to be 3 plus or minus 1. And for the first one, 3 plus 1 gives us 4. And the second one, 3 minus 1, gives us 2. So have to be kind of careful talking and writing at the same time, because sometimes you'll write the wrong thing. Now remember, these are x-intercepts, so they're ordered pairs. The first one is going to be x equals 4, and again, y equals 0. The second one is x equals 2, and again, the y is equal to 0. The y-intercepts are perhaps the easiest points to get on a parabola. We're just now going to set the x equal to 0, which in function notation is calculating g of 0. G of 0 we know is going to be negative 2 times 0 minus 3 squared plus a 2. So that's going to be negative 3 squared, which is 9. This will be a negative 18 plus 2, which is a negative 16. And that's going to be ordered pair 0, negative 16. Sadly, for this problem, we really can't graph that pair because it's way off of the grid, but we know it's out there. So again, 0, -16 is our y-intercept. Next thing to do is talk about max and mins. Probably the best thing to do is graph the quadratic function first and then go back and fill in these three items here. So again, we have a vertex of 3, 2, which will put it 3 units to the right and 2 units up. We know the parabola opens downwards, and we also found x-intercepts of 4, 0 and 2, 0. So our axis of symmetry, again, is that vertical line passing through the vertex. It's always a good idea to label it. So again, that is that x equals 3. And we now have enough information to graph our parabola. So we're going to now go through and just draw through here and back down again. We're not asking for your best artwork, but we definitely want something that looks like a parabola and passes through the points we found. So now let's answer our questions. With regards to max and min, you will notice that since the parabola opens downwards, the parabola's vertex is a maximum. And so that's going to be the location of 3, 2. It's important to specify that the location is the vertex. The maximum value of the function is actually 2. Now for the domain, remember that's the set of x numbers that we can use in the function. In this case, we can subtract anything we want, square anything we want, add or subtract anything we want. So that domain is all real numbers. If you look at the graph, you'll also notice it because it extends forever to the left and right. Now the range, however, is not the same because the graph goes down forever. So it's going to start at -infinity, but it's going to stop at y equals 2 because that's the highest point on the graph. Because we can actually get a value of 2, we use a square bracket to cap off that interval there. So that right there is the first problem, graphing a quadratic function. We'll now move on to our next problem. And our next problem is going to be taking a quadratic function and writing it into that vertex form so we can find all of those different properties we just talked about in the previous problem. Okay, so for our next problem, we're going to put our quadratic function into the special form, which is a times x minus h squared plus k. And you'll notice to do this, we need to complete the square because that formula has a perfect square quantity in it. So this one's going to be a little different than some of the problems we've done before. It's almost kind of like the circle problems that we did where we found the center of them. So what we're going to do first is we're going to selectively rewrite this problem to make it easier to complete the square. In other words, I'm going to rewrite it as g of x is 3 times x squared minus 14x. Then I'm going to leave some room and write down the plus 119 behind it. I'm now going to complete the square inside the parentheses. So I'm going to take half of -14, which is -7, square it, and I'm going to add a 49. So I'm going to add a 49 here, but to keep it equal, I'm going to also subtract 49 so that I have the correct amount. If I'm adding 0, I don't change values. The next thing I'm going to do is I'm going to group the first 3 together, and I'm going to rewrite that as a perfect square. So I'm going to have g of x equal to 3 times x squared minus 14x plus 49. And now when I take that 3 out, you'll notice that it must be multiplied times 49, and that's going to make a -147. So I have a -147 behind this. And of course, I still have the plus 119 hanging out back there. So the next thing we're going to do is now rewrite this as 3 times x minus 7 squared. And then if I combine that -147 and that plus 119, I get -28. So from here, I can now read off my vertex as the ordered pair 7, -1, -28. And my formula again is 3 times x minus 7 squared minus 28. Again, not an easy parabola to graph because -28 is a very large negative number, but we did want to find the vertex and rewrite it in this special form. Okay, so for our next problem, we're going to use what is called the shortcut formula. That's what I call it. And it's basically somebody taking the generalized quadratic function formula and completing the square on it with the a's and the b's and the c's already in the formula. So the x-coordinate, or the h number of the vertex, is found by using negative b divided by 2a. And again, that gives you the first coordinate of the vertex. The y-coordinate just comes from substituting that number into the quadratic function to get the corresponding output. So before we do that, we're going to answer a question about open upwards or downwards. You'll notice there's a positive 3 sitting in front of our x squared. That means that the a number is 3. So if a is equal to 3 and greater than 0, must open upwards. So that is going to be the direction of our opening of our parabola. Now let's go through and use this shortcut formula. So again, the h number is negative b over 2a. So we already said a minute ago that a is equal to 3. The b number is just whatever number follows the x squared, so that's a positive 12. So this is the opposite of 12 over 2 times 3. So that's negative 12 divided by 6, which is just negative 2. So my vertex has a negative 2 for the x-coordinate. Now to find the y number or the k number, I'm just going to substitute that value into my function. So it's f of negative 2. In this case, it's actually m. So let's back up and put an m there. But it doesn't matter what you call your function. You are going to be plugging in a negative 2. So again, m of negative 2. So that's 3 times negative 2 squared plus 12 times negative 2 plus 9. Again, following the order of operations, we square first to get forward, and that makes it 12 minus 24 plus 9. So that's 9 minus 12, which is a negative 3. So that right there is our y-coordinate of our vertex. Remember again, the axis of symmetry is a vertical line, so it's got x equals, and it always passes through the x-coordinate of the vertex. So x equals negative 2. X-intercepts, we go through and we've got our 3x squared plus a 12x plus 9. Remember again, we're setting the y or the function equal to 0. We can divide the entire equation by a 3 to downsize the coefficients. So that's x squared plus 4x plus 3 equals 0. And of course, we could use the quadratic formula to solve this for x, but let's try factoring it. You will notice we can easily find two numbers that multiply to make a 3 and add up to a 4. They're namely x plus 3 and x plus 1. So we get x equals negative 3 and x equals negative 1 as our two x-intercepts. Remember again, those are ordered pairs. So it's negative 3, 0, and it is negative 1, 0. The y-intercept is really easy to find. That's just going to be m of 0. And when the quadratic function is written this way, it's going to be just 3 times 0 squared plus 12 times 0 plus 9. And all you're left with is the c number, which is 9. So 0, comma 9 is the y-intercept, which again is a little big for graphing purposes. The next thing to do is put this all together to graph the parabola. So let's switch over to the next page. So again, we have a parabola opening upwards because remember a was equal to 3, which is positive. So that's going to make this a minimum. So again, that was negative 2, negative 3 was that ordered pair. Remember the domain is going to be all real numbers for every quadratic function, not just the ones we've been looking at. The range we will graph first before we find it. So again, we're going to have a negative 2, negative 3 is our vertex. That's 2 left and 3 down. We also know that negative 1, 0 and negative 3, 0 was the location of our two x-intercepts. We also know we have an axis of symmetry, which again divides us into two equal halves, running right through there at x equals -2. And from there, we can graph our parabola. Again, a very narrow parabola. And now we can list off our range. Our range is going to start down at -3, it's the lowest point on the graph, and go up forever. And again, we include the -3 in our interval notation because that is the point on the vertex. All right, so that was a nice complete graph of our quadratic function. I know I missed the vertex a little bit there in the graph, but good enough, right? All right, now let's go through and do an application problem. So there's a lot of simple business models that can be represented by quadratic functions. In particular, they're really good for studying profit models because of the fact that we have the behavior of things going up for a while, maxing out, and then coming back down again. So we're going to be looking at that for this problem here. So when you're looking at a graph, and especially thinking about the previous page, when the parabola opens downwards, the highest point is a maximum. So we're going to be maximizing our profit here. So this problem says that we have a price P, and when we charge different prices, we're going to have different profits. We all know that if we charge way too little for something, we're not going to make any money. But we also know if we charge way too much for something, people will shop elsewhere and they also won't make any money. So we have to find that nice spot in between where we get the most out of charging the correct price. So for this here, again, we had the formula before, which was H equals -B over 2A. And for us, that's going to be -2560 over 2 times -80. And at this point, I would just put this into a calculator to get a quick calculation of it. And when you do that, you're going to see that you get a -2560 over a -160, and that divides out evenly to make 16. So $16 is the price we should charge to maximize those profits. And again, to translate it into more real world context, if you charge under 16, you'll lose money because you're not charging enough. And if you charge over 16, you'll start losing money because you are charging too much and people are shopping elsewhere. Now to get the maximum profit, that's the Y number or the value that we have at the maximum. That's just the K number from the vertex. So that's F of the number 16. So that's going to be -80 times 16 squared plus 2,560 times 16 minus 17,600. Again, putting that into a calculator, you will end up with $2,880. So that's the maximum amount of money we'll make according to this model. All right, now we're going to talk about the break-even point. And remember, breaking even is where your cost that you're paying out matches the revenue that you're bringing in. So that's where you have a profit of 0. So we're going to set the profit equal to 0, which means that we're going to be setting the F of P formula equal to 0. That's -80 times P squared plus 2,560 times P minus 17,600 equal to 0. When you're dealing with problems like this, it's always a good idea to see if you can downsize the coefficients before you go through and calculate with them. So let's divide the whole thing by 80 and see what happens. Again, dividing by -80 both sides. In doing so, we now get a positive P squared. We get a minus 32P. And then we get a plus 220 is equal to 0. And then from here, we can either use the quadratic formula or completing the square. Again, for review, let's go ahead and complete the square. So that's really a P squared minus 32P. And then we're going to take half of 32, which is 16, and square it. So we're going to add a 256 to both sides. And I did move that 220 over. I just forgot to write that. So again, we're adding the 256 onto both sides. That's just p minus 30, p squared minus 32p plus 256 is equal to the number of 36. We're out of space here, so let's wrap around and continue over here, even though it's kind of messy. Factoring the left side, that's going to be p minus 16 squared equals 36. We can now take the square root of both sides. So that's p minus 16 equals plus or minus 6. So p is 16 plus or minus 6, which calculates to 16 plus 6, which we know is 22, or we have 16 minus 6, which is 10. So we have $10 and we have $22. And what that means is if we charge less than $10, we're going to actually have our cost exceed the revenue, and we're going to have a negative profit and lose money. If we charge more than $22, we are going to have our revenue be too small, and we're going to have the cost be too big, and once again lose money. So it's kind of that parabola shape where you have too high or too low being a bad thing, and the good spot in the middle is where you want to be. Another comment, you will notice that the number 16 is smack dab in the middle between 10 and 22 because their difference is 12. Half the difference is 6. That is 16. So that would make sense because remember, parabolas are symmetric and the vertex always happens halfway in between the two intercepts, which is a nice feature of them. All right, now let's move on to our next page. Okay, so for this next problem, we're going to start off with 144 feet of fencing. We want to build two chicken coops that are next to each other that are rectangles. And so the idea is that we want to use all of the material, the full 144 feet, to build this thing. And we want to maximize the size of them, which is maximizing the area. So the first thing you want to do is think about how you're going to be breaking apart the fencing or folding to build the fencing, if you will. So what we want to do is draw out the two chicken coops like we have here in the picture, and then label all of our sides. So when we label our sides, you're going to see that we have X on both sides and also going up the middle because we have to make sure we put a divider between the two coops to make, between the one coop to make two coops. And then for the Y, we're going to have another Y down here, and another Y down there, and another Y up there. So we're going to have to use all of that material, all 144 feet, to build this, which means that all of those measurements must add up to 144 feet. So if we start adding them up, we'll notice we have a total of 3 of the X's, and we have a total of 4 of the Y's. That must make 144. Now what we want to do next is maximize the area, which means, of course, we need to find a formula for the area. Well, in general, the area of a rectangle is just the length times the width. But we have to be very careful here because our rectangle does have a width of X, but the length of it is 2Y because we have Y twice. So it's actually 2YX. Again, normally it's XY, but because of this partition or division in the middle, we have to have that. Now, the next thing you'll notice is we can't maximize that A formula because it has 2 variables in it. So we need to get rid of one of them. And it's your call which one you want to keep and get rid of. Because we're doing so much with X's in the class, let's stay consistent. So let's solve the formula for Y. So up here, we're going to first subtract 3x from both sides. That gives us 4y is equal to a negative 3x plus 144. Then divide both sides by 4. And you end up with y is equal to negative 3/4 x plus the number 36. That's what I get when I calculate those out. It's just 72 chopped in half again. So now that formula is going to go in place of the y in our area formula. So in doing so, we are now going to have area equal to the 2 that's already there, and then the negative 3/4 x plus 36, which is the y, times the x that's already there. If we multiply that out, and by the way, we should call this a function, a of x, that's going to be negative 3/2 x squared plus a 72 times x. So that is our area function. And what that says is when I have a measurement of x and I substitute it in, I'll calculate the area of the two coops put together. So the next thing to do is now think about how this looks. If I have x equals 0, which means I have a flat coop, I have no area. And then there's a point where x gets so big and the y gets so small that there's also no area. So there's a place in between where I get the maximum amount. Of course, we know that when you graph a of x, it's a quadratic function. It's opening downwards, so therefore the vertex must be the max. So again, that's our thinking. We know this is a quadratic. We know it's a parabola. And when you think of max, you got to be thinking vertex. So that's the logic that we're using there. So again, you could complete the square, but that's a little tough for this one. Why not use the shortcut? So remember, we have our h is equal to negative b over 2a. So that's a negative 72 over 2 times a negative 3/2. And that's just going to equal, with the 2's canceling, 72 divided by 3 is just 24. So that x number is 24. And because we're doing an application problem, it's always good to put units on your answer. So that is going to be at 24 feet. The y number, we can get it a bunch of different ways, but I think the easiest is just to use this formula again, which we have already. So remember, the y number is negative 3/4 times the x we have, which is 24, plus 36. So in this case, that's going to be negative 18 plus 36, which just makes an 18. So that's 18 feet for the y measurements. And then the maximum area, be very careful. We're looking at the maximum area of an individual coop. And I realized when I did this in class, I found the maximum area of both coops. So we should really just be measuring and multiplying the 18 times the 24 to get an individual coop. And that's going to be 432. And those are square feet. So again, I want to acknowledge that is different than what you'll see in the PDF of the notes done in class, because I did both coops added up together in class, which was not reading the problem very carefully. All right, so let's move on and switch out of quadratic functions and now talk about polynomial functions in general. So we'll be back in a couple seconds here to talk about those and discuss some of their brand new properties we haven't seen yet in the class. Okay, so as we start our polynomials, you're going to notice that we have a brand new definition. And the definition is the word 0. And of course, 0 does represent the number 0, but in this case, we're going to talk about zeros of a function. And the 0 of a function is any number you would substitute into the function to get a y value or an output of 0. So it's basically numbers that make 0, if you will. And so zeros are going to be found the easiest way by factoring. And sometimes you can just, when they're factored, you can look at them and just read them right off the graph. For problem number 6, however, you'll notice it's not factored, so it's not as easy to figure out what the zeros are. If you're kind of keen on calculating in your mind, you might see that 0 does make the function equal to 0, and we will see that in our factoring as well. So let's first factor this down. And in factoring it, remember you should always try to find a greatest common factor first. And you will notice that all these numbers are even, so 2 goes into them, and you will also notice they have a factor of x. So let's take out the GCF of 2x. When you do that, you will now have a 5x squared plus a 3x minus a 2. I'm using square brackets in here because our leading coefficient is a 5, and so we're going to use the AC method to factor it. So when you use the AC method, remember you take the first and last number and you find their product. So we know that 5 times negative, I just did it in my head, 5 times negative 2 is negative 10. That makes it negative 10. And you want to find a pair of numbers that adds up to make a positive 3. And then it's going to be a plus 5 and a minus 2, the original pair that got us into these numbers in the first place. Remember now, the next thing we're going to do is rewrite that middle number using them. So that's going to be plus a 5x minus a 2x minus a 2. And then we've got a 2x. And now using grouping the first 2 and the second 2. From the first, we can take out a 5x. So we've got a 5x, leaves me with x plus 1. Back there, I can take out a minus 2, leaves me with x plus 1. And technically, that sign should be changed at that point. And then we can rewrite this as 2x times x plus 1 times 5x minus 2. And at that point, we don't need those square brackets. We just got 2x times x plus 1 times 5x minus 2. So now to get our zeros, we just set each of those zeros, or I should say all of those zeros, factors equal to 0. Sorry, the word will come out. I just got to keep pushing. So our first 0 actually comes from the number 0. The second 0, you'll look at it, is negative 1. That comes from taking x plus 1 and setting it equal to 0. So negative 1 is that 0. And then finally, if you take a 5x minus 2 and set it equal to 0, you get a 2/5. So those are my 3 zeros there. We'll talk a lot more about multiplicities in the minutes ahead, but for right now, the multiplicity is the number of times the factor shows up when it's factored. It's the number of times it's repeated. So the x is to the first power, multiplicity is 1. The x plus 1 is to the first power, its multiplicity is 1. 5x minus 2 shows up to the first power, its multiplicity is 1. So when a factor just shows up by itself, it is a multiplicity of 1. For this next problem, you'll notice that it's pre-factored already, which is really nice. So we can just list off the zeros by looking at it. For the first one, it says that x is equal to 0. For the second one, it says that x is equal to 1. And then finally, for the third one, it says that x is equal to 2. Again, that's just either setting x minus 2 equal to 0 or just inspecting that substituting a 2 in would make that factor 0 and the whole thing equal to 0. All right, so for this problem here, we've got a 0 of the number 0, 1, and 2. The multiplicity on x equals 0 is 4 because that factor is to the 4th power. The x minus 1, that's to the 1st power, so the multiplicity is 1. The x minus 2, that's raised to the 4th power, so that multiplicity is 4. We're going to be talking more about this in a few minutes here, but if you were to actually multiply all of that out, you will get a 9th degree polynomial. That'll be the power on x, and that's actually the sum of the 3 different multiplicity values we have. So you'll notice that the degree of the polynomial, which is the highest power that shows up, is going to be the sum of the multiplicities. So we'll see more of that in the coming minutes. Let's move on now to the next page. So the next page is going to be all about the behavior of polynomials when you graph them. When we're graphing and studying polynomials, you will notice that there are going to be 4 different possibilities for what's called end behavior. And the end behavior is really what happens in the 4 different quadrants where it either starts or it ends. So for example, when you have our odd degree polynomials, they will always start and end in different places. They do not start and end at the same. So when it's a positive leading coefficient, which remember again is the number in front of the highest term, when it's positive, it starts down at negative infinity and ends at positive infinity. So you have that nice little split behavior we talked about. When you multiply by a negative or have a negative coefficient, if you will, that's going to flip it. So it starts at positive infinity and ends at negative infinity. However, when you have a even degree polynomial, numbers like 2, 4, and 6 powers, they always start and end at the same place. And when it's a positive leading coefficient, it always starts up and ends up. So it starts high and ends high. And then when it's a negative leading coefficient, it's just flipped upside down. So it starts low and it ends low. So remember that odd degrees, first degree, third degree, fifth degree, seventh degree, they start and end in opposite directions. And when it's an even degree, like 2, 4, 6, and 8, it always starts and ends at the same direction. So what you can do is have a pretty good idea what the graph looks like with the end behavior just by studying the formula for the polynomial. So for number 8, you will notice that it's a 6-degree polynomial. So the degree is equal to. All right, so again, in this case, the degree is 6. That's the highest power showing up in the polynomial. And that is an even number, which means we're in the one of the two second cases. We're either going to start high and end high or start low and end low. Now, it all comes down to the leading coefficient. So the leading coefficient, that's equal to a negative 1/3, which is negative. So that puts us in the second category, which means it's going to start low and it's going to end low. By the way, if you have a polynomial that is not in the proper order, it's always a good idea to put it in descending order with the powers counting down before you answer such questions. Otherwise, it gets really confusing. All right, so the next one's a little more challenging because it is showing up in a factored form. But what you want to do here is you want to look at the powers on each of the factors. The x plus 1 shows up to the first power, so it's 0 is going to have a multiplicity of 1. The second factor is a third power, and then the last one is a first power. Summing up those powers is a 5th-degree polynomial, which is odd. Another way to think about it, if you're to multiply all of that stuff out, which we're not asking you to do here, you would get 5 as your power on x. So that's an odd degree polynomial. The next thing to do is think about leading coefficients. Again, we really don't care about the value of the coefficient. Rather, we care about the sign of it, whether it's positive or negative. But if you were to multiply all this out, you would have a 2 from the first one. You'd have a 4 to the third power from the next one. So that'd make a positive 128, which is greater than 0, which is positive. So for this problem, we have an odd degree, and it has a positive leading coefficient. So it's that first picture up there in the chart where we're going to start low and we're going to end high. And again, this could be verified as well by plotting a few points near the end of the graph or looking at a graphing program like Desmos or a graphing calculator. But the idea here is to really know what's happening just by studying the formulas for the functions. All right, so now let's move on to the next page. And the next page is going to be about what's called the intermediate value theorem. Okay, so as we talk about the intermediate value theorem, we're discussing this because we want to start graphing and building nice pictures of polynomials. And to do that, we want to know all the different properties that they have. So we just saw on the previous page that they have different end behaviors depending on the degree and the leading coefficient. The next thing to talk about here is going to be how the graphs actually look when you draw them. And the graphs are always going to be continuous. If you go out to take calculus one day, you'll spend a lot of time discussing that. But at the college algebra level, the idea is to have more of an intuitive idea. So the idea is if I drew the graph from left to right, I would never have to pick up my pen or pencil, and I would have a nice connected graph. More importantly, polynomials are also smooth, which means that they're going to be nice and curved graphs. They're not going to have any corners on them, no breaks or holes in the graphs, no vertical asymptotes, which we talk about in the coming weeks. They're just nice, smooth, continuous pictures that flow across the graph. So because of that, we can talk about what's called the intermediate value theorem, which says that if you have values on both sides of a graph, you could always find a value in between because it's a continuous graph. In other words, if I have a function value here and a function value here, I'm guaranteed to have points everywhere in between because I know that I'm not going to have any breaks or holes in my graph. So that's useful for people trying to find zeros of a polynomial, because if I know I go from a negative number to a positive number, I must pass through 0 because every value is represented in between. So this is kind of a way to help us hunt down and track zeros when you're studying functions. So for this next problem, we have a polynomial called c of x, and we want to see whether or not the theorem says that there's going to be a 0. It's important to understand this theorem does not rule out zeros. In other words, a sign change that doesn't happen doesn't mean there still can't be one somewhere in there. It just might mean that we picked two bad numbers. So again, if we have a sign change, we know there's a 0. If we don't have a sign change, it's inconclusive. So for this problem here, we want to go through and calculate the function values and see how they compare. So for starters, let's take a look at the interval 1, 2. I'm going to calculate c of 1 and calculate c of 2. C of 1 is just 2 times 1 cubed minus 14 times 1 squared plus 8 times 1 plus 10. C of 2 is just 2 times 2 cubed minus 14 times 2 squared plus 8 times 2 plus 10. When I calculate those, which I probably want to do on a calculator to save some time, the first number is a 6, and the second number is a negative 14. 6 is greater than 0, negative 14 is less than 0. So because of that, we know that there must be a 0 in between those two numbers. There could be more than one, but we know there's at least one there. So down here, I'm going to circle yes. I know for sure there's at least 1 0 on that interval. Now let's take a look at the next one. The next interval is 2, 3. So I need to calculate c of 2 and c of 3. Well, I already calculated c of 2 a few minutes ago, and I got a negative 14, which we know, of course, is less than 0. Now let's calculate c of 3. That, again, that's going to be 2 times 3 cubed minus 14 times 3 squared plus 8 times 3 plus a 10, and that calculates out to be a negative 38, which we know is less than 0. So this intermediate value theorem is going to say that nothing really. It's going to say that it's inconclusive. Because I don't have a sign change, I don't know what's going on. Again, a sign change implies a 0. No sign change means that we need to either pick a new interval and find out what's happening, or just give up on this interval for right now. So the answer is no. The theorem does not imply a 0 on that interval. Again, doesn't rule it out, but it doesn't guarantee it. That's what's important to understand about this special theorem here. All right, let's move on now to the next page. And this is where, in my humble little mathematical opinion, the fun begins. We're going to start putting the graphs and the formulas together to start seeing how things fit. So for this first problem, we want to look at how we can take the graph of a polynomial and find out all of its properties of its algebraic formula. And in fact, you can write down a candidate for its formula just looking at this graph. So we'll do that in a few minutes here. All right, so for our first problem here, the goal is to find out as much information as possible from the graph of a polynomial. And one of the themes you'll notice in graphing polynomials is always starting with the zeros. They tell us the most information possible. So the zeros, again, are where the function's going to cross the x-axis, and that is where we have the x-intercepts, and we know that comes from setting the function equal to 0. So again, the logic is setting the function equal to 0, is where the y equals 0, and that's the x-intercepts. So we can just read them. So the first one you'll notice on the graph is going to be at the point x equals -3. The next one happens at x equals -1, and then the third one is x equals +1. So that's our 3 zeros, -3, -1, and +1. Now, believe it or not, you can actually get the multiplicity from the graph, or at least have a pretty good idea of it. So you'll notice here that when you're at -3, that line, or that part of the graph, not line, but that graph crosses through like a line. It's almost linear, if you will. Because it's crossing like a line, it's crossing to the first power. So therefore, the multiplicity is 1. Again, when a graph crosses through the axis and it appears like a line, locally speaking, it is multiplicity 1. The same thing happens over there when x is -1. It crosses through like a line with a positive slope. However, you'll notice when you get to x equals 1 over there on the right side of the graph, locally speaking, this kind of looks like a parabola. You know, as it kind of comes down, touches the axis, and then bends away again. So locally, it looks like a parabola, which we know is a second power thing. So the multiplicity there is 2. And now, when you add up the multiplicities, you will get the degree of your polynomial. 1 plus 1 plus 2, it makes 4. And 4, recall, is an even number, which has end behavior, starting and stopping, high and low, same place. It's high, either both high or both low. In this case, it's both high, obviously, since that's where the graph starts and ends. Next thing to do is think about the leading coefficient. Again, we don't have an idea what the number is, but we can definitely tell the sign of it. Because it's starting high and ending high, we know that it must be a positive leading coefficient. And again, 4 is an even number, so that's our degree. So we can get all that information from that picture. What's even more fascinating is we can now start writing out a formula for the polynomial based on the zeros. Because x equals -3 is a 0, if you add 3 to both sides of that, x plus 3 must be a factor. So x plus 3 is my first factor in my polynomial. Because -1 is a 0, I know that x plus 1 must be a factor. And because 1 is a 0, I know that x minus 1 must be a factor. But the multiplicity is 2, so it's squared. The next thing to do is notice that, since I have a positive leading coefficient, I can be safe and put any positive number there. You could be pickier, however, and actually figure out what number it crosses on the y-axis. But for right now, let's not bother with that. Let's just leave it as a positive 1 in front of it, just to kind of keep it simple. The next problem will make it a little bit more complicated, and we'll talk about that in a minute. So now let's move on to the next polynomial. You'll notice first we start with the zeros. So coincidentally, -3 and -1 are zeros again, but now the number 2 is a 0. So I'm going to list those out in our table. So we got -3, -1, and 2. You'll notice that for all 3 of those x-intercepts, it crosses like a line because it goes running right through and doesn't bend away. So those are all multiplicity 1, which means that the degree, which is the sum of those numbers, is a 3, because 1 plus 1 plus 1 is 3. So therefore, we're going to have an odd degree polynomial. But you will notice this time around that the graph is starting in a positive place, up here. Positive infinity if you keep going forever. The only way negative x numbers are going to give you a positive is if you have a negative leading coefficient to go with it. Or again, just refer back to your chart. So this leading coefficient is actually negative because we have it starting high and ending low. So that right there is our formula for our, that's not our formula, it's our answers. All right, now let's build our function. And we saw earlier that when negative 3 is a 0, x plus 3 is a factor. We saw that when negative 1 is a 0, x plus 1 is a factor, and x minus 2 must be a factor when 2 is a 0. Now we're going to take and deal with this really important point over here. You will notice the graph crosses through at 0, 3. At 0, 3, that means that's the y-intercept. So that means that x must be 0. So if I was to stick a 0 in these three spots, I would have 3 times 1 times negative 2, which is negative 6. Well, sorry, negative 6 and 3 are not the same thing. But the question is, how do you turn a negative 6 into a positive 3? Well, obviously you need a negative number, and you need to cut 6 in half to make 3. So that leading coefficient is negative 1/2. Now what's really nice about this is you can test out your theory by plugging in 0 again and see if it makes it true. And a 0 in there will make positive 3 for the y number. Also, you'll notice that negative 1/2 is going to make a negative leading coefficient. So again, this makes sense logically. Everything's meshing. So again, negative 1/2 is the value of the leading coefficient because we want the graph to pass through 0, 3. You can also force it algebraically, and we'll do that next week when we start looking at Note Quiz 9 and polynomials in more depth. But for right now, we're just kind of doing this by inspection. Let's move on now to the next page. And the next page is going to have us taking and drawing polynomials based on their formulas. So the idea, again, is to kind of go through, analyze the formula, and piece all of that information together. So let's kind of go through and start recording some information. Again, I like to personally start with the zeros because the zeros tell most of the story. And we'll also write down the multiplicity behind them. So the first 0 here, you will notice, is negative 4, because if I plug in a negative 4, I do get 0. So negative 4 is my 0. The multiplicity there is 2, because that factor is squared. The next 0 I see is the number 3. It shows up to the first power as a factor. Multiplicity is 1. 1 is a 0, and its multiplicity is 1 because that factors to the first power. We're now going to plot those zeros. So I'm going to plot negative 4 on the x-axis. I'm going to plot 3 on the x-axis and 1 on the x-axis. The next thing to do is talk about the degree. So my degree is going to be 4 because that's the sum of my multiplicities. So my degree is equal to 4. And now the leading coefficient is a little harder to do, but still not impossible. You'll notice if I multiplied all this stuff out, I'd have a negative 1/6 in front of the x to the 4th, which is less than 0, which is negative. So I'm going to have a graph where it's going to start low and it's going to end low. So I'm going to put little low arrows here and low arrows there. So now I'm going to come up and draw this graph using the multiplicities. Now remember, we're not really focusing on how high or low the y numbers are. We're focusing on really the zeros and the shape. So I'm going to start low. And of course, it's a continuous graph with no breaks. I'm going to hit the negative 4 and bend away. I know that because the multiplicity is 2. It's going to be locally a parabola. Now, as I extend from left to right, I'm going to be heading towards that 0 at x equals 1, and I'm going to cross through like a line. So again, I'm not going to worry about how high or low I am. I'm just going to cross through right there. And now because I have to cross through at 3, and it's again a multiplicity 1, I'm going to come through and cross like that, and then connect up to my end behavior down there. And now if I piece everything together logically, it is an even degree. It starts and ends in the same place. It's upside down because of the negative leading coefficient. And I've got the 3 zeros in there represented with the multiplicities accurately represented. So pretty nice how you can kind of sketch a graph without having any kind of graphing technology. All right, so let's move on now to the next problem. And the next problem is going to be another graph. You'll notice this time around, however, that it's not factored. So I can't just get the zeros from looking at it. You will notice, however, that I can do factoring, and then the factoring will tell me my zeros. So this function has kind of a quirky name. It's called t of x, but we'll let it go for now. You'll notice greatest common factor, taking out an x squared, leaves me with a 4x cubed plus an 8x squared minus a 25x minus a 50. Because I have 4 terms in this factorization that's left over, I should probably use square brackets instead. So let's go ahead and rewrite that as 4x cubed and end it with square brackets. Because remember what 4 terms means, grouping time. So let's go ahead and group. I'm going to group the first 2 together and the second 2. And when I put a parenthesis there behind that minus, better change that to a plus so that stays a negative when I multiply it. All right, so now again, I still have my leading x squared. Inside here, I can factor out a 4 and an x squared. Leaves me with an x plus 2. Back there, I can take out a 25. Leaves me with x plus 2. So I've got an x squared. And then taking out the common x plus 2, I'm left with 4x squared minus 25. And you'll notice that I can now factor that with the difference of squares. And I don't need the square brackets anymore. So that's just an x plus 2. Using the difference of squares, that is a 2x plus 5 and a 2x minus 5. So it looks like we have a total of 4 different zeros here. The first one you'll notice is the number 0 is a 0 because there's a factor of x leading the way. That multiplicity is 2 because it's an x squared. The next 0 from looking at it is negative 2 because plugging in negative 2 will make that whole thing 0. The multiplicity is 1. The other ones, maybe a little side work will help us get them. If you take a 2x plus 5 equal to 0, that means 2x is negative 5. So x is negative 5 halves. A very similar calculation over here gives us 2x minus 5 equals 0. So 2x is 5, dividing by 2. X is 5 halves. So that's my other 2 zeros. I've got a negative 5 halves and a 5 halves. And both those factors show up to the first power, so their multiplicities are 1. Now, what's nice about this form, which is sometimes called the expanded form, it is pretty obvious my degree is. My degree has got to be 5, which we know is an odd number. We can also read off the leading coefficient without doing any work at all. The leading coefficient is just 4, which we know is greater than 0, which is positive. So because I have an odd degree polynomial with a positive leading coefficient, I know it's going to start low and it's going to end high. It must. All right, next thing to do, plot those zeros. So my first 0 happens at the number 0. I have one at negative 2. I've got one at negative 5 halves, which is negative 2.5, which is right there between negative 2 and 3. And then my last 0 is at 5 halves, which is positive 2.5. All right, so now we're going to draw the graph of this. And again, we have to make sure we draw a nice, smooth, continuous graph. And we have to make sure we honor those multiplicities. So my graph is going to come up, cross through negative 5 halves, and bend right back away again at negative 2. Again, it's going to go above the axis and back down through again. Let me draw that a little nicer because I got a little shaky there with the drawing part of it. All right, so let's see if we can get that a little nicer. All right, again, up and then through. That's about the same. All right, so now let's go through and approach 0. The multiplicity is 2 at 0, which means that as we come up and up to the 0, we have to hit it and bend away from it and not cross the x-axis. And then we have to cross one more time at 5/2, which is 2.5. It's going to come through and cross like a line and cut straight through to the end behavior. So that right there is a good sketch of our polynomial. Again, we're not sure how high or low it goes unless we were to plot a bunch of ordered pairs and do those calculations to see where it goes. But that's how we do a crude sketch of a polynomial. In the next note quiz, we're going to spend some time trying to find the zeros algebraically by doing some division and some factoring, and also using what we know about the graphs to see when we can find zeros. So a lot more about polynomials to come.